G'day viewers. In this video presentation we're going to investigate a possible mechanism for interstellar travel based upon Bob Lazar's story. As with the previous episode, what you'll see here is conjecture. Our entire explanation could be incorrect, so viewer discretion is advised. The first point I want to make is that although the title of this presentation refers to faster than light travel, we don't mean it literally. It's a figurative description only. You'll understand why as we move forward through the solution. The second point I want to make is that we'll ensure that we don't break any standard physics rules as we move forward. The way we're going to do this is by assuming that our human understanding of physics isn't wrong, it's correct, but it's incomplete. What do we mean? Well, in episode 16 we revealed that faster than light travel is impossible, which can be proven via space-time diagrams, as presented by Cool Worlds Lab. Not only do they prove that faster than light travel is impossible because it introduces time paradoxes, but they also prove that instantaneous travel is impossible because it introduces time paradoxes as well. This means that utilising wormholes is also problematic. I highly recommend that all viewers visit the Cool Worlds Lab YouTube channel. I'll display the appropriate link shortly. Hopefully, if you've watched our previous episode, that is episode 54, you'll remember that we proposed a mechanism relating the operational principles of element 115 to the quantum vacuum. You should remember that we talked about baryonic matter evaporating into the quantum vacuum, that is, the dark reservoir of quantum potential energy via a conduit. We identified this conduit as being the fourth spatial dimension. If you have not already seen the previous episode, please set some time aside to watch it. It'll help with your comprehension of key concepts in this episode. On screen you can see a four-dimensional hypercube, also known as a tesseract. Illustrating a 4D object in a 3D world is literally impossible, so the image you see on screen is a shadow, that is, an approximation. To make matters worse, try generating a similar approximation for a sphere yourself. See how far you get. What you end up with is a conceptual mess. What you get is known as a hypersphere. This is enough to hemorrhage your brain. In cosmology, we think of the observable universe as being a sphere. We think this because our scientific observations see across the same distance in all directions. Hence, we form an observational sphere around ourselves. But surely there must be a better way to approximate, represent and communicate our cosmological interaction with the fourth spatial dimension. Well, as it turns out, there is a better way to do this, and we'll be looking at that soon. Okay, let's now walk through our solution with the aid of some graphics. The first thing we're going to do is eliminate what is impossible. We know that interstellar travel is required, but we also know that faster than light travel introduces paradoxes and therefore is impossible. Please take the time to follow the link shown and watch the video. It shows that all forms of faster than light travel are impossible, and the authors of the video have done an excellent job presenting the evidence using only space-time diagrams. So, if faster than light travel isn't possible, interstellar space travel is also impossible, right? No. Another possibility exists, and we'll look at that a bit later on. But before we move on to our solution, let's do a quick review of one of Hollywood's favourite interstellar travel solutions, that is, wormholes. Even though the Cool Worlds Lab have already dismissed the idea of wormholes utilising space-time diagrams, I think it's important that we shoot the idea in the head again, but this time utilising general relativity. In truth, the bullet we'll put into the gun on the next slide is meant as much for general relativity as it is meant for the idea of wormholes. Okay, let's take a look. Wormholes naturally emerge from the equations of general relativity. Albert Einstein and Nathan Rosen published a paper in 1935 describing these wormholes. However, they were found to collapse so quickly that not even light could pass through them. To keep wormholes open, it was postulated by Kip Thorne that exotic matter would be required. Exotic matter, which does not exist, would need to exist in the form of negative energy or negative mass. Although the concept of negative energy is permitted within standard physics, it simply doesn't make any intuitive sense. The fact that the mathematics works isn't convincing enough to believe it can exist. Don't forget, negative energy means negative mass. Quite frankly, negative mass is a Hollywood concept. It's not real life. What the required condition of exotic matter tells us is that general relativity is simply the wrong tool for interstellar travel. If you're not already convinced of this, don't forget that GR did not predict the existence of dark energy or dark matter, both of which have been experimentally confirmed. Nor did general relativity predict accelerated cosmological expansion. In fact, Einstein assumed the existence of a static universe and mathematically forced the solution to be static. He couldn't have been more wrong. This tells you something. It means that general relativity's predictive capability has been limited to baryonic matter, which is only about 5 to 6% of cosmological mass. It also tells us that general relativity works great on an astronomical scale, but cannot be considered reliable on a cosmological scale. The consequence of this is that Albert Einstein and general relativity are 94 to 95% wrong. I don't see how anybody could argue differently. It's a fact that general relativity only explains about 5 to 6% of the observable universe, but what about the other 94 to 95%? This clearly demonstrates the knowledge gap we presently have with general relativity. The takeaway point here is that general relativity is not the answer to everything. Okay, let's shift gears and move back to something we talked about earlier. Let's look at our cosmological interaction with the fourth spatial dimension, that is, the dark reservoir of quantum potential energy. The standard model of cosmology conceptualization of the universe appears on screen. It's intuitive, simple, and very easy to comprehend. However, it is profoundly limiting. A significant problem with this representation is that it does not visually communicate any aspect or even the existence of the quantum vacuum, let alone the quantum vacuum ground state, that is, the zero-point field. The standard model of cosmology representation of the universe is derived from general relativity. Unfortunately, the future of cosmology is not general relativity. The future of cosmology is the integration of general relativity with quantum mechanics. The most obvious integration point between these two disciplines is the quantum vacuum. It is important to note that in the standard model of cosmology conceptualization shown, the diameter of the sphere denotes the size of the observable universe, that is, approximately 92 to 93 billion light years. Illustrated on the right-hand side of the screen is the quantum model of cosmology. The quantum model of cosmology is an equivalent representation of the standard model of cosmology, but also includes the quantum vacuum. The quantum model of cosmology is a sphere of Hubble radius enveloping the quantum vacuum, specifically the quantum vacuum in its ground state, termed the zero-point field. The radius of the sphere changes with Hubble time, and the observable universe rests upon the surface of the sphere. This means that, in order to circumnavigate the observable universe, a traveller must move all the way around the sphere, returning to their starting position. By doing so, the traveller has moved approximately 92 to 93 billion light years, which is equal to the diameter of the standard model of cosmology conceptualization on the left-hand side of the screen. In other words, the perimeter of the quantum model of cosmology equals the diameter of the standard model of cosmology. As you can see, our conceptualization of 4 spatial dimensions is significantly easier to grasp than a cosmological hypersphere. Most importantly, we have included a representation of the quantum vacuum ground state, that is, the zero-point field. This is something that the standard model of cosmology does not do. On the next slide, we'll take the quantum model of cosmology one step further. An important aspect of cosmology which has not been adequately addressed by the scientific community is the relationship between the zero-point field, also termed the quantum vacuum, and the 4D space-time of general relativity. In this illustration, we split the quantum model of cosmology into 2 representations of space-time. One of these is termed Hubble, the other is termed observational. Hubble space-time is a sphere of Hubble radius, such that the Big Bang occurred at its centre. However, equally importantly, the zero-point field in this illustration is also located at the centre, expanding at the rate of the Hubble constant, h sub phi. In Hubble space-time, our physical universe exists on the perimeter of the circle, with the observational radius indicated by the semicircular arc A to B, which is approximately 46 billion light years. Consequently, the observable universe is represented by the complete length of the perimeter of the circle from A to A, which is approximately 92 billion light years. You can see from the magenta box that Hubble space-time and observational space-time are geometrically synchronized. So, what is the relationship between these two illustrations? The relationship is that Hubble space-time is an extra-dimensional representation of cosmological expansion adjunct to observational space-time. In recent years, it has become clear from increasingly accurate measurements that the Hubble parameter obtained by cosmic distance ladders cosmic distant ladder techniques is significantly higher than the values obtained by fitting the power spectra of temperature fluctuations in the cosmic microwave background radiation. This difference has been termed the Hubble tension. The Hubble tension is represented within these illustrations. Depicted inside the Hubble space-time sphere, we see the Hubble constant relating to the power spectra from the cosmic microwave background radiation, and term this the cosmological Hubble constant, appearing as h sub phi. Similarly, depicted within the observational space-time sphere, we see the Hubble constant relating to the cosmic distant ladder, and term this the astronomical Hubble constant, appearing as h sub double phi. When we merge the white sphere with the gold sphere, we get 5D spacetime, or in other words, 4 spatial dimensions plus 1 temporal dimension, and we come back to the quantum model of cosmology illustration we saw on the previous slide. Please pause the video to study the information provided. Okay, now that we have conceptualized the present-day universe in terms of 5D spacetime, let's turn the clock back to the instant of the Big Bang. In episode 9, we derived 5 key conditions at the instant of the Big Bang. As you can clearly see, these are exact analytical solutions, which is always a good indicator of validity. We achieved this by utilising a 2020 publication by Storti, whereby the author accurately calculates an experimentally verified value of the Hubble constant as measured via the cosmological power spectrum. This information is transformed into the Big Bang singularity radius. The result obtained indicates that the Big Bang singularity radius, that is, the size of the universe at the instant of the Big Bang, was approximately 4 times the classical electron radius. The two most useful results going forward are the mass density and size of the singularity we identify as existing at the instant of the Big Bang. Historically, cosmologists believed that cosmological inflation commenced at the instant of the Big Bang. Nowadays, the prevailing view is that the Big Bang followed a period of cosmological inflation. However, our construct has demonstrated that the Big Bang and cosmological inflation period occurred concurrently. That is, we have demonstrated in numerous publications that the Big Bang and cosmological inflation were not serial events, they both occurred together. In other words, the Big Bang was a specific event during the cosmological inflation period. Consequently, at the instant of the Big Bang, the radius of the universe was approximately 12 femtometers, that is, about 4 times the classical electron radius. Let's now start tying everything together in terms of interstellar travel. On slide 2, we presented evidence created by others, clearly demonstrating that faster-than-light travel of any form generates physical paradoxes. Hence, the concept of faster-than-light travel may be dismissed as nonsense. Importantly, the creators derived this conclusion utilising space-time diagrams, so the method of faster-than-light propulsion is irrelevant. If faster-than-light travel is physically impossible, could wormholes be possible instead? Unfortunately not. Wormhole travel introduces the potential for paradoxes as well. How so? Well, in the video created by the Cool Worlds team, they allow for instantaneous travel too. This is pretty much what wormhole travel is equivalent to, instantaneous faster-than-light travel. Hence, it is also impossible and can be dismissed as nonsense. So where does this leave us? Well, unfortunately, it doesn't leave us in a good place. All we can do is wishfully assume that the physics of today doesn't have all the answers and some room for movement exists. This is why the solution for interstellar travel presented in this episode is pure conjecture and open to refutation and correction. Having said this, let's take a crack at it anyway. In our attempt, we'll approach the problem in a new way. Throughout numerous episodes, we have proposed the concept of the Big Bang singularity. This is not a new idea, but we have given it new life. I would encourage viewers to review our video titled History of the Cosmos, which was presented at a conference hosted by CERN in December 2022. In our presentation, we show that the Big Bang singularity remains a valid proposition, despite contemporary assertions contesting this. The significance of this is that, at momentarily prior to the Big Bang, every point in the universe was, simplistically speaking, co-located. We have also propositioned in episode 6 that the zero-point field denotes a dark reservoir of quantum potential energy. Hence, combining the concept of a Big Bang singularity with the quantum model of cosmology, we propose that any 2 points within the quantum vacuum which are in precisely the same energy state will be separated by the distance as occurred at the instant of the Big Bang, that is, no more than the singularity radius appearing on screen. This may not be as bizarre as it sounds. The Large Hadron Collider in Switzerland have claimed to have reproduced the conditions of the Big Bang, but fleetingly. If true, then they have made our point for us. It becomes entirely conceivable that element 115 as an energy source could be capable of this, or indeed much more. Let's try to visualise what we mean. Let's begin by considering the concept of gravitational equipotential. In this illustration, we see the Earth from space. The polarizable vacuum field is the polarized form of the quantum vacuum. In other words, the polarizable vacuum field is a quantum vacuum representation of the curved spacetime associated with general relativity. The dotted line represents an arbitrary orbital radius. Every point along this line is at the same gravitational potential. This means that, in a manner of speaking, every point along the line of equipotential is the same point. Hence, in a manner of speaking, a satellite travelling along the orbital circumference hasn't moved at all, only time has passed. Let's now look at a space alien civilization, perhaps 39 light years from Earth. Let's also assume that their home planet had the same mass as Earth. If the Martians were visiting Earth and wanted to go home for dinner, how might they be able to do this with element 115? If they wanted to travel from point A to point B, then in some sense these 2 points are co-located because they're at the same quantum potential with respect to the quantum vacuum. So if these 2 points are at the same quantum potential, as a consequence of quantum vacuum polarization induced by the presence of planetary matter, what lays between them? That's easy to answer: the dark reservoir of quantum potential energy. The dark reservoir of quantum potential energy is represented by the ground state of the quantum vacuum, termed the zero-point field. This means that between point A and B exists a randomized effervescent field of virtual photons popping into and out of existence. This is also known as the Casimir effect. If element 115 acts as a quantum vacuum inhibitor and can eliminate the Casimir effect between 2 points in spacetime, it may mean that the spacetime between these 2 points collapses so that the endpoints become effectively co-located, as was the case momentarily prior to the Big Bang. This means that, at most, the space-time between A and B is no more than approximately 12 femtometers apart. This is not to say that a wormhole has formed between these 2 points. We mean to say that they are almost literally the same point in space-time as might have appeared momentarily prior to the Big Bang. And, as we know, creating Big Bang conditions is possible, as claimed by the team at the Large Hadron Collider in Switzerland. So, what rules can we infer from this conjecture in order to avoid paradoxes? Let's discuss this on the next slide. Let's begin by looking at the change in the quantum vacuum from the Big Bang to the present day. We know from claims by the Large Hadron Collider team in Switzerland that reproducing the conditions of the Big Bang have already been experimentally accomplished. The fact that humanity is able to achieve this at our current level of technology is a guarantee that a more advanced civilization elsewhere in our galaxy must also be capable of similar achievements. However, the claims of Bob Lazar permits the latitude for space alien Martians to accomplish this, but without a particle collider and in a more efficient manner. Perhaps they have achieved this utilising element 115. If so, we propose that element 115 acts as a quantum vacuum inhibitor, collapsing spacetime between 2 points by destructively interfering with the Casimir effect. This, in effect, achieves a similar outcome to the Large Hadron Collider team in Switzerland by reproducing a geometric attribute of the Big Bang, but at a micro scale. Since no 2 points in spacetime can ever be determined to exist in exactly the same state at the same instant, as inferred by the Heisenberg uncertainty principle, the natural connection of points can only have ever occurred once in the history of the cosmos, that is, at the instant of the Big Bang. However, perhaps it is possible to connect 2 points utilising element 115 technology by inhibiting quantum vacuum probabilities. However, this would also come with its own set of difficulties. For example, the quantum vacuum state of the target destination would be required knowledge, hence polarizable vacuum structured environments such as planetary gravitational fields might be preferred. Random quantum vacuum environments such as free space may not be desirable or possible, but that's not all. In order to avoid paradoxes, time may need to dilate across the throat of the bridge. Thus, some of the rules required in order to avoid paradoxes might be: number 1, only one-way travel is possible, that is, in the direction of motion. Number 2, time dilates as if the distance A to B was being traversed at near the speed of light, hence no time paradoxes. And number 3, the entropy of the universe continues to increase due to natural cosmological expansion. So, if points A and B are separated by 39 light years, the journey home for the Martians aboard the spaceship will appear almost instantaneous, as if stepping through a doorway. But to observers on Earth, approximately 39 years will have passed. Of course, as we stated at the very beginning of this presentation, this is all purely conjecture and we may be completely incorrect. Moreover, criticism of our solution should be tempered by the fact that all forms of faster-than-light travel, including wormholes, have significant paradox issues of their own. Therefore, the solution we have presented is no worse than any existing proposition, including those presented by Nobel laureates. Let's summarise what we have learned. In this episode, we have covered the following key concepts. Firstly, all forms of faster-than-light travel are physically impossible. The team from Cool World's lab have proven this utilising space-time diagrams, so the specific method of faster-than-light propulsion is irrelevant. For all possible forms of propulsion, faster-than-light travel is a physical impossibility because it introduces time paradoxes. Secondly, instantaneous travel mechanisms such as wormholes are also a physical impossibility. This means that general relativity as a physical theory is useless because it requires the existence of exotic matter. The fact that general relativity can be made to mathematically work by Nobel laureates such as Kip Thorne contradicts the conclusions derived by the Cool World's lab team utilising space-time diagrams. Therefore, general relativity may be discarded with respect to interstellar travel theories. However, we have proposed a possible solution which does not violate the space-time diagrams defined by Cool World Labs. Our solution does not result in instantaneous interstellar travel. Time is dilated in accordance with the requirements of standard physics. Moreover, by avoiding general relativity, we have avoided the requirement for exotic matter. We have also proposed that some of the rules required to avoid paradoxes might be: number 1, only one-way travel is possible, that is, in the direction of motion. Number 2, time dilates as if the distance A to B was being traversed at near the speed of light, hence no time paradoxes. And number 3, the entropy of the universe continues to increase due to natural cosmological expansion. Thus, we propose that element 115 acts as a quantum vacuum inhibitor, suppressing the Casimir effect. Hence, simplistically speaking, no Casimir effect equals no space-time curvature. This literally means that the distance between 2 points collapses to a separation of no more than 12 femtometers if the Casimir effect between them has been cancelled. So, in summary, we have established a possible explanation for the manner in which element 115 may permit interstellar travel based upon quantum mechanics, specifically quantum probabilities. However, once again, we stress that the contents of this episode are purely conjecture. The conclusions presented may be incorrect, so viewer discretion is advised.